All right, time? Okay, question 1, describe linear interpolation. Okay, so I'm going to start from this side today. You guys. Yes. Whoever represents your group. Okay, so if you are given 2 data points, linear interpolation is going to work between 2 data points. You have x1, y1, x2, y2, and you're trying to find a value in between. So that's where linear interpolation works. Okay, given n data points or data point pairs, so x1, y1, x2, y2, collection of points. What is the order of the polynomial that interpolates these data? You guys. Yes. N minus 1. Yeah. Can you clarify why?
Because there's the constant that is not multiplied.
Yes. Okay, and we'll get to that after the last question. So I explain why. So polynomials are nonlinear. They have x cubed, x squared, x cubed, x to the fourth, right? So they're obviously nonlinear. So how come when we do a nonlinear polynomial fit, so a cubic, let's say, how come when we do that, we have to solve a linear system of equations? So, you guys. Yeah, but what are we solving for? So we have x squared, x cubed, etc. So how come we have linearity although we have non-linearity? So where did you get the linearity from? Yes, because we are solving the coefficients. Yes, for the coefficients. So, although the polynomial is nonlinear in x, very good, you should be happy. Yeah, you got that. So although the polynomial is nonlinear, although the polynomial is nonlinear in x, it is linear in the coefficients because the coefficients are just a0, a1, a2, and so on. And when you think about interpolation or the data fit, you are given the values for x. So you are given x squared and x cubed and so on. When you substitute those values in, there's just going to be constants. And the unknowns, you're going to be linear in the unknowns, which are a0, a1, and a2, and so on and so forth. Okay? So that goes back to the answer your colleague gave. Why do we need n minus one polynomial for n data points? Because remember, we have this a naught constant in the polynomial that doesn't multiply anything. So for a quadratic, you have a naught plus a1x plus a2x squared. So you have 3 data points, right? Okay. For those of you who exit the class when I ask these questions, and I know who you are, you're losing the opportunity to learn from these questions because these questions are going to be, some of them are going to be on your exam. So don't do that. I'm not going to deduct points or add more points to you if I ask you a question and you don't know the answer. Just tell me, hey, I don't know the answer, and that's fine. We'll move to another group. But the purpose here is to learn, right? So these questions are important. And yes?
Can you say one more time the third question? It's because the coefficients on the nonlinear polynomial are. Sorry, could you say it one more time?
Yes. Okay. So just to finish up on the other point, if I happen to pick you and you don't know the answer, just tell me I don't know the answer. I'm not going to deduct points of you, and don't be embarrassed about this. This is about learning here. What's more important is for you to stay and listen to the answer for these questions, okay? Okay, so I'm going to show you this equation here. So we said we were going to fit a polynomial of this form, a naught plus a1x plus a2x squared, etc. Ask yourself, what do we know and what do we not know here? Do we know the x values? We want the polynomial to pass through each and every data point. These data points are given to you. You are given x and the value of y, the value of the polynomial. So if the polynomial is passing through these points, then we know the values of x. So once you put in the values for x, so imagine you are taking this polynomial and applying it at x1 and x2 and x3, etc. what are you left with? You're left with the coefficients only, a0, a1 as the unknowns. And that's a system of linear equations. So the polynomial is in a way linear in the coefficients, but nonlinear in x. But since you're given x here, then that nonlinearity is just kind of washes away into the values. Okay? Is this clear? Should be on this slide. These slides should be up on my website. So essentially, we just take, this is another example, you take the polynomial and you evaluate it at the different data pairs for x1, x2, and x3, and then what you're left with are the unknowns, a0, a1, and a2. Okay. So last week we left off at cubic splines, and I had explained kind of the idea of deriving cubic splines. They're a little bit involved, so we're not gonna go ahead and implement cubic splines ourselves. We're just gonna use the functionality that is built in Python. And we went over the number of constraints that are needed, kind of the general idea of cubic splines. What I wanted to do today before we leave the topic of interpolation is to show you a bunch of examples for the different types of interpolants. And I gave you a bunch of recipes of how to use linear interpolants, polynomial interpolants, and cubic splines. So just feel free to use those in your homework. You should be able to just copy paste from the slides as text into your Jupyter notebooks. Okay, so what we're gonna do is actually a demo, and one of your colleagues asked me last week if they can do like a user interface in Python. So there are some features in Jupyter notebooks that allow you to embed elements of a user interface, like a slider or a text box, etc. They're called widgets, and part of kind of a fancy Python Python module. So I'll show you one type of one demo for interpolation. Okay. So just give me a second, please. So what we're gonna do now to test how well data interpolates, we're gonna mimic data that we're gonna create. Okay, we're gonna create, let's say, a Gaussian function. We know that Gaussian function. We're gonna create that, but then assume we don't know that Gaussian function, and only sample a bunch of points from that function. Give those points to the interpolant, and see how well we can reconstruct the original function. Does this make sense? So maybe I'll show you this slide to kind of clarify things for you. What we're gonna do, we're gonna create a function like this one, a Gaussian function. We're gonna take that function and just sample random points in between. Pick a bunch of points, this guy, that guy. Get the value, evaluate those points using the full function, and then take those points, give them to an interpolant. So as far as the interpolant is concerned, you only have these discrete data points. Okay? And then try to reconstruct the original function with the interpolant and see how well they compare. Okay, it's a great test. Okay? So let's do this and kind of set this up for you. It's got some fancy Python stuff. Don't worry about this. This is just a demo. Okay, so we're going to start with a Gaussian function. Okay. So what I have here is a Gaussian function. That is the original function. Imagine you know the data, what it looks like. So that's the original function. But in reality, you don't know what it is. And now imagine you are given only 2 points for this data. You're given just these 2 points at the end. Then linear interpolation is going to give you this line. And then same thing for polynomial and cubic spline, because that's kind of like the degenerate case. They all go to linear interpolation. What if you were given 3 points? Okay, look at that. You're given 3 points. This is what linear interpolation does, and then what cubic splines and polynomials do. Polynomial and cubic spline, in this case, they're kind of on top of each other. Okay, but linear interpolation, obviously, with 3 points, is just going to connect them with straight lines. Now, again, remember that the true function is this guy in the black solid line. But imagine you are given only these 3 blue points. Okay? So obviously, with more points, we're gonna do it better. We're gonna follow the original function a little bit better. Now we have 4 points, then 5 points, and then let's say 8 points. So the more points you add, look at what happens to linear interpolation. Linear interpolation starts to follow the original curve very well, and so does the spline. The spline is in green. But look at the polynomial. It's really badly behaving at the ends, right? And we saw this last time. Because as you increase the order of the polynomial, you're going to get more wiggles. Why? Because the higher the order of the polynomial, the more roots the polynomial has. So therefore, the polynomial has to go up and down to cross the x-axis. And it just so happens, with the higher the order, is going to mess up your interpolation. And this is really bad. If you go even higher, let's go like 12 points, you see linear interpolation is starting to do much better, except here around the peak. Kind of messes things up. Cubic splines are a perfect fit. I mean, we nail the distribution with cubic splines. They're really good. But then the polynomial is still badly behaving near the boundaries. Okay? So if I do 13 points, see what happens at the linear interpolation with the linear interpolant. Now we go to more and more points. Look at that. Starts to get better and better. Now what's happening to the polynomial, if I plot this outside the -1 and 1 domain, the polynomial is going to behave really, really badly. So let me see if I can reproduce that. So let's go from -2 to 2, and then do this again. And hold on. Something. So -2 to 2. Okay. See the polynomial. Look at the polynomial. It's really bad. Okay? And then you get this polyfit may be poorly conditioned, right? Which we saw last time. Okay. So now let's pick another function. Is this clear? Is it clear what I'm doing here? So I have an original data function, an original function. I'm going to assume I don't know it. I'm just going to pick points from that function, give it an interpolant, and see how well we can reconstitute the original function. It's a great way to verify and see how interpolants behave. So I'm going to give another function now, so I call it hyperbolic Gaussian, which is a Gaussian distribution with a hyperbolic tangent. Okay? I'm going to run this. I'm going to start it at 2 points. Okay. So the original function, the original data, should follow this black solid line. You see, it starts at -1, goes flat, and then, bam, it peaks, and there's a little kink over here. Please. And then goes up, and then flattens out again. With 2 data points, all linear and polynomial and cubic splines, they just follow the same line. Obviously, a pretty horrible interpolation. Okay? So now let's start adding more points. So 3 points, 4 points. This is interesting, but obviously we're missing the curve, right? 5 points, 6 points, 7 points, 8, 12, 13 points. Well, the spline is doing much better. The polynomial is horrible, and in fact, the linear interpolant is impressively good, except around this kink here. That's going to be the worst nightmare for the spline and the linear interpolant, but the polynomial, I just give up. And then if you continue doing more points, you start seeing how these interpolants dance around the function. So look at what happens here. We're getting better around the kink. Linear and spline interpolants nail these regions, but polynomials do not. So use polynomial interpolants very carefully. Okay? Try to limit it to a quadratic, where you have just 3 points you're interpolating at, or use splines if you can, and linear interpolation. If you have a lot of data, linear interpolation is really great. So if we had a lot of data clustered around this kink here, then the linear interpolant would nail it, would get it really well. Okay? And that's just sort of a demo of a comparison between all of these. Okay, and I have graphics for this in the slides, showing you the Gaussian function. As you increase the sampling points, you get a better representation of your data. Obviously, this guy that follows the hyperbolic tangent and the Gaussian, of course, the polynomial is just horrible. Splines are better. Linear is much better. And a bunch of other examples. So bottom line, cubic splines is usually quite accurate and cost effective. Linear is quick and easy, especially when you have a lot of data points. I'd always try linear. Polynomials, you have to be very careful. I would leave polynomial interpolation to the end. So why did we learn about it? Because it is interesting. It teaches us how to do spline interpolation, shows you how linear systems show up, and it still can be used in many cases. If the data is truly polynomial, then you can get a polynomial interpolant and call it quits. Okay? And this ends the discussion on linear interpolation. I'll put up your homework for linear interpolation on Thursday, so that we have enough time before the midterm. Remember, your midterm, you're gonna cover everything until today. Okay? On Thursday, we will start with a beautiful topic of regression analysis, and we'll do linear regression and a bunch of other things, and we start seeing kind of more usefulness of numerical methods. Okay? Thank you very much.